A wonderful occasion at the beginning of a new conference. I was actually one of the program co-chairs for the very first iClear 2013 in Arizona. Now these days, iClear is broken into the top 10 most impactful venues according to Google Scholar. So I think actually not many people remember now that actually the first iClear was teeny. It wasn't like this at all. We had an audience of about 120 people that showed up for that very first iClear. So this conference is on to a really impressive start, and I wish all the organizers equal growth patterns to iClear in the years ahead. Okay, so I was a little bit worried giving this keynote because I was thinking to myself, who should you take your LLM wisdom from in 2024? Should you be taking it from me, or should you perhaps be taking it from someone like Jason Wei or any of a number of other people in their 20s? And you know, I think the honest truth is that there are quite a lot of questions about large language models for which you can get a lot better answer from a whole lot of people in their 20s than from me. So I thought I should lean a little bit into the side of things where wisdom maybe gives me an advantage. So for the first half of this talk, I wanted to give some fairly general and historical remarks about the emergence of language models and where things might be on questions of meaning and intelligence. And then the second half, I'm going to move into some recent work with my PhD student, Shikhar Murty, on building web agents using large language models. So my very first NLP conference was in 1993. It was ACL 1993 at The Ohio State University. It wasn't in a grand room like this. It was in sort of like a regular lecture hall that held about 200 people. And the conference had 33 main conference papers. I don't actually have any photos of it, so this isn't a photo of it. This is a recreation, but it shows the essential piece of technology of that time, which was the overhead projector. An audience participation question, so you can wake up and stretch. Who in the audience has actually seen an overhead projector? Okay, that's all of the older people in the audience. Just put their hands up. Yeah, so you used to get these pieces of plastic that you either hand wrote on or printed from a laser printer and stick them. Oh, it was terrible. Anyway, but you know, at the time, this seemed a really exciting time in NLP. It was the time when empirical data and probabilistic methods, then generally known as statistical NLP, were exploding on the scene. And so this first conference, my paper, was presenting on statistical NLP. But here's another audience participation question. Of the 33 papers that were at this ACL, how many were about language models? How many people, so 33 papers in total, how many people think that 10 were about language models? How many people think that 5 were about language models? How many people think that 3 were about language models? How many people think that 1 was about language models? How many people think that 0 were about language models? Okay, it's the zeros that are correct. There are precisely no papers at ACL 1993 that were about language models. If you asked the easier question and said, how many of these 33 or the lower threshold question, how many of these 33 papers mentioned a language model? The answer to that was there were 2 papers. So there was Pereira, Tishby, and Lee, who recently got an ACL Test of Time award for their work on distributional clustering of English words, and that they mentioned that this clustering might be useful for building class-based language models. And Black, Jelinek et al. From the IBM Statistical NLP group mentioned n-gram language models, pointing out the limitations of the context that they could handle as part of motivating their approach to probabilistic parsing with history-based grammars. So with 2020 hindsight, this is a pretty surprising state of affairs. Why was no one working on language models? It's not like language models were a new thing in 1993. I mean, like, how exactly were people expecting to get to artificial intelligence? So the origin of language models, or more famously for most of the world until 2020, the origin of Markov chains, was Andrei Markov's work in 1913 on transition probabilities between letters in the verse novel Eugene Onegin. It wasn't exactly a character-level language model, since actually he was only distinguishing vowels and consonants. So it was kind of like a two-class, class-based bigram model in retrospect. Then after that, around 1950, was Claude Shannon's breakthrough work in information theory. In PyTorch today, when you invoke cross-entropy loss, you're still paying homage to Claude Shannon's work. But he also built both word-level and character-level n-gram models of English. However, I think one has to say the real origin of language models as we know them now, and certainly the term language model for referring to a probability distribution over next words or utterances of a language, is worked in Fred Jelinek's group at IBM in the 1970s. And these language models were already being proven really useful in areas like speech recognition. So why wasn't anyone concentrating on language models almost 20 years later in 1993? I think to some extent people don't have the history right in their heads with respect to what the language situation was like. I think what tends to have dominated in people's mental model is the computer vision story. And when I was at a bunch of 20-year-old tech startup people the other week, the vast majority of them said that making progress about AI was principally about data. And I think that's kind of the story that people have learned from computer vision, where sort of a simplified story is essentially there were sort of 50-odd years of computer vision research where people worked with minute amounts of data and hand-built edge detectors and things like that. And then in the second half of the 2000s, there started to be minute-sized modern-style labeled data sets, things like the Pascal, VOC, Caltech 101, or CIFAR 10. And then in 2010, eventually there was data. There was ImageNet with a number of labeled images in the millions and 1,000 classes, and that's what led there to be foundation model for vision that worked, and that for object classification to be, quote, solved. But that's not actually really how the picture looked like in NLP. So here's the history of large language models in NLP. As far as I'm aware, the first mention in academic work of the trigram large language model is actually in 1998. It's a pretty obscure paper, CPAT tree-based language models with an application for text verification in Chinese, and what they're interested in was how to do efficient indexing of a large language model of trigrams built over 200 million words. In 2000, came out Yoshua Bengio and colleagues' famous neural probabilistic language model, which really kicked off neural language models. But that wasn't large. They built it on 32 million words, down an order of magnitude. Then in 2007 was the first really famous large language model, and it's right there in the title. But this generally came to be known as the Google Ngrams corpus. So Thorsten Brantz and colleagues at Google built an n-gram model up to 5 grams over a 2 trillion token corpus. Then in 2018, GPT and BERT came out, which I think most of us these days think of as the sort of first large language models. They were in a 3.3 billion token corpus. And then in 2020 onwards, we have the sort of big models of today, 100 billion plus parameters, trained on 1 trillion tokens or more, GPT-3, 4, Palm, Llama 3, you know all the players there. So if you look at this picture, it's sort of more complex. So for the first neural language models, I think really that their problem was not enough compute. And I slid this over so you could see the 31K vocab, right? That they were artificially limiting the size of the vocab. This was before the days of subword models, so that they could keep the matrices smaller, right? Lack of compute. But once you get to 2007, there wasn't any lack of data. Look, they had 2 trillion words. Their problem was that they didn't have enough model flexibility. Then in 2018, when GPT and BERT came out, well, maybe there the problem was not enough data. We thought they were pretty good at the time, but we didn't really get the exciting results of today because that was only 3.3 billion tokens. And then all of these came together in the 2020s, and language models became the exciting things that we know today. In some sense, I'm just restating Rich Sutton's bitter lesson that general methods that leverage computation are ultimately the most effective and by a large margin. But, actually in that quote, the 2 things that Rich really emphasizes are the flexible model and the big computation. In his telling, data is mentioned because big compute allows learning on huge training sets, but it's sort of just in the background rather than really being independently emphasized at all. So, with hindsight, we clearly should have been pushing large language models much earlier. We could have built much bigger and better things in the 2010s, and we just didn't. And the question was, why did no one push that? And I think it's fairly clear why that is. That in the 1990s or the 2000s, we actually already regarded language models as great and useful things. We used them for speech recognition, predicting word sequences, spelling correction, machine translation. The language model was always the most useful part. For fluent natural language generation, we used them for all sorts of things, but nobody thought of them as something that could give you language understanding, the meaning of sentences. So how did people hope to build artificial intelligence? It wasn't by improving language models, because language models were just statistical things. They didn't understand language. And so everyone basically accepted the idea that what we needed to be doing was building a mapping towards an explicit semantics. And some people still think that's the case. At this point, I think it is clear that they're wrong. As the model scale grows, large language models start to build internally models of the world which enable them to understand text. I think for a lot of the people in this room, this is just manifested in an informal way. You use language models, and to a large extent, they just understand what you're asking them. It's just obvious that they understand language. But for others, this is a quite complex philosophical argument, and I'm just going to be able to very briefly summarize where that stands today. So most well known in the NLP world is the work of Bender and Kohler 2020. And so Bender and Kohler argued for a classic form of there being a distinction between form and meaning, which has been pretty standardly seen in linguistic formal semantics or in Anglo-American philosophy of language. So Bender and Kohler write, linguistic meaning is the relation between a linguistic form and a communicative intent. The language modeling task, because it only uses form as training data, cannot in principle lead to learning of meaning. So, this is sort of really kind of a strict logical thing, right? Language models, you've got forms, sequences of forms. You're not building a mapping to meaning, therefore there can't be meaning. And that's the basis of their referring to large language models as stochastic parrots or synthetic text extruding machines and other colourful metaphors. More formally, in terms of philosophy of language, I take this as the internalist conception of meaning, that understanding consists of mapping to some internal representation in response to linguistic input, a representation that is somehow different to the language itself. This was the perspective that was already parodied in Ludwig Wittgenstein's 1953 Philosophical Investigations when he wrote, "You say the point isn't the word, but its meaning. And you think of the meaning as a thing of the same kind as the word, though also different from the word. Here the word, there the meaning, the money and the cow that you can buy with it. But contrast money and its use." A variant of this position, but still involving mapping from form, is the classic referentialist position in philosophy of language, which has dominated a lot of recent linguistic semantics, where we attempt to ground meaning in the world. So the meaning of horse is the set of horses in the world, or the meaning of yellow is the set of yellow things in the world. So this might suggest that a plain language model has no notion of meaning, but a vision language model does. Somehow we give a certain sort of primacy to certain kinds of sensory evidence, even though everything ends up as electrical signals in the brain of roughly the same sort. But would we really want to say that a visual language model captures meaning, but a pure large language model doesn't? Some people have actually suggested that, but to me, that seems kind of crazy, especially when in 2024, as we all know, visual language models are still surprisingly blind. So I think we want to say that large language models do have meaning inside them. So the final alternative position that's been staked out in philosophy of language is often referred to as either inferentialism or pragmatism. So it's the kind of position Wittgenstein adopted when he said that for a large class of cases, though not for all, in which we employ the word meaning, it can be defined thus: the meaning of a word is its use in the language. So inferentialism couches understanding as appreciating the appropriate versus inappropriate ways to use language in context. So that's often summed up as a use theory of meaning. Now, I should point out, some people don't accept this to this day as a good theory of meaning, but I think it fits much better with the models we're building in the LLM world. So when we think about it this way, our context might be visual, the real world, they might be textual, conversational, sociological, etc. The real world may be in some sense privileged, but it's not the only context for grounding meaning. We also have virtual worlds, we have language contexts. This is also essentially the notion of meaning that Turing argued for in his book, in the same book that the Turing test was introduced, perhaps more for practical reasons than anything else. And under this notion, I think what we want to say is that meaning is gradient. You can partially understand appropriate context for use of a word without understanding everything that anybody knows about appropriate context of use of a word. So I've used this example of these different ideas of partial knowledge of meaning for the word Shanai. So what is a Shanai? Well, one possibility is you can have seen one or held one, and then in some sense you have a classic grounded meaning for Shanai. If you haven't, I could at least show you a picture of one. That's what one looks like. But if I wasn't going to be showing you a picture, sorry, I left out a bit. But a picture's something, but surely you'd know more about the appropriate context of use if you'd actually heard the instrument played. And if I'd never seen, heard, or felt one, but on the other hand, someone gives me a definition, like a traditional Indian instrument, a bit like an oboe, right? Surely that gives me some meaning for this word, even though it's purely textual. It gives me a reasonable approximation of appropriate context of use. If they added more information, holes like a recorder, multiple reads, then I'd have more meaning for understanding what this means. So then, if we jump across to what's more like the language model training case, that we wouldn't get a definition, but we'd get context of use. So in Anuradha Roy's book, An Atlas of Impossible Longing, this sentence appears. From a week before, Shanai players sat in bamboo machans at the entrance to the house playing their pipes. Bikash Babu disliked the Shania's whale, but was determined to fulfill every conventional expectation the groom's family might have. Now, in some ways, I understand the meaning of the word Shanai less from this passage than someone who has seen one. I don't really know exactly what it looks like, but I still know it's a pipe-like musical instrument. But interestingly, I actually in other ways know more about appropriate context of use than someone who has seen a Shanai, because I know important musical and cultural information that someone who's simply seen a Shanai would lack. Okay, so that's meaning. I wanted to go on and then say a few words about intelligence. I think it's fair to say that in the popular imagination, since ChatGPT, large language models have essentially become synonymous with artificial intelligence. If you're reading something in the paper or a news clip and they talk about artificial intelligence, they mean a large language model, which for people who have been in NLP for a long time is a really weird thing. Right, for all of the rest of the last 30 years until ChatGPT came along, NLP was some kind of weird appendage of AI and machine learning that no one paid too much attention to and we kept to ourselves or something like that. Well, what are people meaning these days by artificial intelligence? So the artificial part is easy. What is intelligence? And is language understanding and generation distinct from general intelligence? Tuesday afternoon, you're going to get Ev Fedorenko around, and maybe she'll address this because she has a recent paper with Kyle Mahawald and others, which tries to argue from neuro-linguistic evidence for a distinction between language processing and more general cognitive processing. I'm not actually sure I buy all of their argument. They sort of end up taking a very narrow view of what counts as linguistics, so it's only the form part, whereas it seems to me that many parts of language processing, like pragmatics and sociolinguistics, are part of language, but sensibly also recruit generative cognitive processing abilities. But let me move on for now to this question of intelligence. So, I'm your emissary from the California Republic. You've probably been hearing a bit about how there are various AI-focused bills in the current California legislative session. The one that was most well-known and controversial, SB 1047, didn't get approved by the governor, but a whole bunch of other bills are now California law. And it turns out that one of those bills defines artificial intelligence for the state of California. And this is the definition given. California AB 2885. Artificial intelligence means an engineered or machine-based system that varies in its level of autonomy and that can, for explicit or implicit objectives, infer from the input it receives how to generate outputs that can influence physical or virtual environments. I think a lot of these definitions that you're seeing of artificial intelligence have enormous problems. And I think one of the easiest ways to see the problems of many of these definitions is what I introduced to you as the landmine test. Now, I'm as much in favor of regulating landmines as anybody else, but I would hold to you that the landmine completely satisfies this definition of artificial intelligence, and I kind of don't actually think that landmines are artificially intelligent. So it seems like somehow we want to refine things from that. And I think a lot of the time we have problems with our definitions of intelligence, even with human beings talking about other human beings. I think in retrospect, we've often made mistakes in what we regard as intelligent. So, we think of, GPT-4 as intelligent because we can ask it what's the capital of Bhutan, or tell me the chemical formula for methane, and it knows the answers to all of these things. And I think it's true that historically we tended to think the same for human beings. If someone knew US law really well. We say, oh, they're really smart. They've got an encyclopedic knowledge of US law. But that's not really intelligence. That's sort of knowing a lot of facts like an encyclopedia knows a lot of facts. And then another one you see a lot is sort of ability to do tasks. So one of the common definitions of AGI you see bandied around is ability to perform most cognitively or economically valuable tasks at or above the level of the average person. So that suggests that if I had somehow built a good task performing machine, that it's somehow intelligent. And I don't think it has to be so, because we have lots of task performing machines like, calculators, and they don't seem terribly intelligent. So another definition that's widely cited is Legenhutter's one, an agent's ability to achieve goals in a wide range of environments. One I came up with for a document at HAI was the ability to learn and perform a range of techniques to solve problems and achieve goals appropriate to the context in an uncertain, ever-varying world. And I think there's something very important here, which is I think you can only claim to have intelligence if you have the ability to be adaptive to different environments and to learn as you go so you can operate better in different circumstances. And from that kind of perspective, if perhaps only for practical deployment reasons, we're not actually really getting that notion of intelligence in the current commercially available large language models. Yes, we have input context stuffing where we can give them a certain bit of current information to help guide what they produce next, but they're not actually really adapting and learning as they go about the world. And so often it seems like what we have in an LLM is still that we've built this enormous simulacrum, that it has enormous amount of knowledge of the past world that is mined from all of our human collected knowledge. And so it looks on the surface like these machines understand the world and how it works, but it's not clear that they can generalize outside their training distribution. It's not clear that they can learn about the world as it changes. And often when we poke a bit, we see places where they reveal that they don't understand. Now, at this point, I have to admit that, you have to stay current with these large language models. They keep on getting better, and we can only predict that they're going to get better and better in the coming years. So, back a couple of years, like in the days of DaVinci 002, it's really easy to show, this model doesn't really understand. If I give it a simple reasoning thing, the cost to produce a book is $1,000 plus $8 per book. The book sells for $20 each. How many books must be sold to make a profit? It says 1,250 books. Obviously doesn't understand. But we were clever in those days. We knew you could get better results by saying, let's think step by step. So I put that in, and then it did steps, a lot of which seem reasonable, and it's probably getting too small to read, but actually it gives the right answer at the bottom, and so you might think it's great, but unfortunately if you look up a couple of lines, it makes this wonderful move in the proof from minus 1,008 is less than 12n to 1,000 is less than 12n, which is the kind of new creative math that they teach in California schools, but wasn't a step you were meant to make when I was young. But this is just no longer the case. If I throw this example into GPT-4o, not only does it now format it beautifully, as you can see on the right, even though it's small, it gets things like this 100% right. This was another of the sort of more spatial reasoning things that the models used to get wrong. If the town of Twee is 12 kilometers from the town of Wallop and the town of Golis is 18 kilometers from the town of Twee, what is the maximum minimum possible distance the town of Wallop is from Golis? Nowadays GPT-4o gets this exactly right, shows the correct reasoning, works out that the minimum can be 6, the maximum is 30, understands spatial reasoning, it's amazing and great. Except, still not quite really. Because if you just make this a fraction more complex, and you add a fourth town, the town of Ansel, that's 5 kilometers from the town of Golis, and then ask how far apart are what can Wallop and Ansel be minimum and maximum, it gets the maximum right, 12 plus 18 plus 5. But then for working out the minimum, it somehow decides it's going to subtract 5 from 30 and comes up with 25. I mean, this still isn't a very hard problem, right? I think, this is something a 7th or 8th grader could do and get the right answer. We're not exactly into PhD level physics problems yet. So the question then is, will we be able to solve intelligence by simply scaling up our current model architectures? At the moment, we're clearly getting things that look more like reasoning and intelligence by scaling things up, but will we truly be able to solve system 2 thinking, deeper reasoning, deeper search, deeper thinking things through? Or will we always have some kind of surface interpolation, a simulacrum? If you're interested in these issues, there's the first workshop on System 2 reasoning at scale that's going to be coming up NeurIPS and should be an opportunity for more discussion of this issue. So what is the answer to this? I think no one working on language models up till 2015 understood how far you would be able to push word sequence learning to push the state of the art of understanding. Many people thought many things were impossible. Quite a few of you probably remember this little clip from Jan LeCun. Uh-oh, we had sound when we practiced it and now we don't. Oh, I know, I probably did not choose the right sound output. External headphones. Okay, we'll have one more go.
Don't think we can train a machine to be intelligent purely from text. So for example, I take an object, I put it on the table, and I push the table. It's completely obvious to you that the object will be pushed with the table. There is no text in the world, I believe, that explains this. And so if you train a machine as powerful as it could be, your GPT 5000 or whatever it is, it's never going to learn about this. That information is just is not present in any text.
It's a funny clip, and I think it is true that Jan LeCun has been sort of biased against language and large language models and has made too strong claims. But part of me kind of tends to think that Jan is maybe actually right. I myself remain skeptical that we can just build larger and larger language models, and that's actually going to give us the deeper understanding and reasoning models, system 2 thinking that we actually need. But, I think it's just unclear, right? That, I think what we're playing out at the moment is effectively the linearization of representation hypothesis. So no matter what we want to do, we linearize it into a long sequence that we put into a transformer, and we make the transformer big enough, and we see what it can do. We throw in lots of data, of course. And, I think it's clear already that this linearization hypothesis has taken us further than anyone realized. So, who would have thought that vision transformers, just turning an image into a raster linearized stream of patches, would work as well as they've turned out to do? Or if you've been watching some of the interviews recently about OpenAI's O1 model, Noam Brown, who used to be involved in doing things like search in AI, said, well, what we realized is we could just start having a long enough linear sequence And the model, you can linearize a proof, right? You don't have to have tree-structured exploration and do search. You can always re-represent a tree as an unfolded linear sequence. And we could just give it a long linear sequence, and it could start to embed search across a graph within that linear sequence. So will that be able to push us all the way? I sort of think that we still need to be skeptical of that. But on the other hand, something that I said more than a decade ago now, when people were very skeptical about deep learning around 2011, when we were first doing it for language, what I would say then was, that deep learning seems to be a really rich vein of ore that we've found. And I don't really know how far this vein of ore extends, but it sort of seems like the most productive way to make progress at the moment is to dig in the direction of the vein of ore. And it seems like 13 years later, that still seems to be the case, that we don't know how far it'll take us, but it still seems the most productive thing to try and pursue. So for the remainder of this talk, I do want to get on a bit and say about some current technical work, which is some work on learning grounded instruction following web agents with the help of language models. This is work with PhD student Shikhar Murty. So far we've thought of language models basically as text completion engines that can be adapted to a wide range of NLP tasks. An LLM gives a distribution over next words in a textual context. But can we use them as a policy for following instructions in grounded environments? One possibility is to directly prompt a language model to behave like a language condition policy. Given a goal, an observation, all the actions the model has taken so far, we can prompt it to come up with the next action using chain of thought. But fundamentally, the problem with this is that a language model just may not know how to carry out next actions because it doesn't have context about a new website. Websites keep changing, and the model might not know the exact sequence of steps to do complex tasks like cancelling a subscription without a lot of test time exploration. But moreover, remember we want our models to learn, so we don't also want our model to only be able to work on Amazon. We want it to be able to adapt, so it could also work on Temu or Espresso Parts or whatever other website we want to use. So somehow we have to learn some context to teach a language model to carry out actions on a website. Where might that context come from? Well, if you follow the decades of work on ground instruction following, we might think of collecting human demonstrations. But the problem with that is human demonstrations are costly. There's tons and tons of websites. But humans can just learn how to use websites by playing around with them. So is it possible to do that with models, i.e. not providing any human demonstrations? So our first attempt at doing that was Bagel. The general idea was we wanted to play around to produce synthetic demonstrations with an exploration policy that is a prompted LM. We give this exploration policy an action space, and it takes actions one at a time. As it takes actions, the website state changes, and so the observation changes, and so you get sequences of actions leading to trajectories. Now the question is, once we have these trajectories, what do we do with them? A lot of trajectories might not even be meaningful, so we need to work out what are meaningful interactions. The idea here is we use our large language models. We use a second prompted large language model, a trajectory labeler, that looks at a trajectory and tries to assign a natural language instruction that the trajectory might be following. If we do that, we get the kind of instructions are labeled here. Book a flight from SFO to New York City. This is the model trying to guess things. It may not be right, so that one's not really right because the trajectory doesn't show a complete flight booking. So to deal with that, we're going to introduce the demonstration filter. So the demonstration filter is very simple. It's going to take the generated instruction, the trajectory, and assign a score based on how well the trajectory corresponds to the instruction. Once we run the demonstrated filter, we see that some of these instruction trajectory pairs are good, and so we add those as synthetic demonstrations. But some of them are bad. And so the second technical novelty is, instead of discarding these instruction trajectory pairs, we're going to do a refinement procedure that's kind of like back translation and machine translation. We're going to take the generated instruction and try and run it out as a new trajectory. And then whatever's produced, we're going to attempt to label again. And so we're going to go around in a loop like that and try and find a pair of a label and demonstration that succeeds in making it through our filter. But sometimes we just don't succeed, and it just keeps on running and doesn't work, and so then we'll stop after a fixed number of iterations. Our first experiments with this were with running this on the MiniWoB data. This is kind of a sandbox environment that evaluates basic browser interaction capabilities for social media browsing, replying to emails, booking flights. It's not really a real-world benchmark, since it's a fairly limited space. But nevertheless, it's a commonly used evaluation. And we can see here that using this idea of in-context learning with Bagel demonstrations significantly improves across the performance of a zero-shot language model. Remember, the zero-shot model doesn't have any context of how to operate on new websites. And so having the benefit of these exploration-guided demonstrations is giving us about 15% better performance. There are other baselines we can look at. A common alternative is just to fine-tune based on having instructions and generating synthetic demonstrations, an instruction-first model. That's not as effective as doing an exploration-first approach. It scores about 9% worse. The other thing we clearly gain from is that iterative refinement, where we go back and forth of trying to refine our synthetic pairs. That gives us about 8% better performance. Let's see, maybe I'll just skip that to rush ahead. But we wanted to go on from there to consider grounding instruction following on real websites. Exploration in Bagel worked for simple demonstrations, but real sites and real tasks are more complex. So you might have something like on GitHub of navigate to the issue titled memory leak for the VLM project, like the comment by a particular user, and then respond to the post saying, I am also able to blah, 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 blah. And so let's see what kind of linguistic prior we could use for that. Coming back to that example task, we can look at a trajectory for it, and what we observe is it involves subtasks. So the first subtask is navigating to a particular repository on GitHub, and then there's a second subtask where we open the issues page, and then we go on and navigate to a particular issue, and so on. And so we can use the fact that there's this structure of subtasks to guide our exploration for learning good synthetic examples. And so we can explore that in the new, much better environment by Graham Nerbig and colleagues of WebArena. So for our neural netscape navigator approach, we explore and work out different stages of the trajectory are good tasks. And if they turn into bad tasks, we can then cut off our exploration at different points. As a result of that, we can save a lot of search, more effectively guide our exploration, and also more effectively find much better explorations because they have the structure of tasks with hierarchical subtasks. And so we can get out very interesting and lifelike complex tasks in our synthetic demonstrations. And again, we find the same kind of result. I'll skip that one. We find the same kind of result, that by making use of doing the exploration first, we can significantly improve our performance in doing Web Arena tasks. I should be stopping here, but this is the kind of ways in which we can then automate the rollouts from the model for closing an issue in a repository, making a comment on a post, creating new discussion forums on a Reddit-like site, following directions on maps, adding items from prior orders to a cart, or interacting with an inventory. Okay, I'd better stop now. Thank you.
Yeah, we have time for questions. If you have any questions, please come to one of the two microphones. Yeah.
Hi, Chris. Oh, there's no mic yet, I don't think.
There is now.
Hi, Chris. This is an amazing talk, as always. Thank you very much. This is Ari Holtzman from U Chicago. And I was just wondering about kind of combination of the first half and second half of your talk. You're talking about what language models can know and how they appreciate meaning. It seems that we test meaning in terms of capabilities, especially in terms of kind of short input-output pairs. But it seems a big part of human meaning, of appreciating the appropriate use, is going about goals and actually appreciating them in trying to actually complete goals or having a drive towards certain things. And it seems like we have to rein in language models a lot, exactly what you're talking about here, about reining in exploration, because it's not actually goal-driven. Do you think that has anything to do with this debate about how much language models understand? Or do you think we'll always be able to describe things in terms of these kind of input-output pair tasks?
That's a good question. Yeah, I might have to think about that some. I mean, I think you are right that there's a problem there. I mean, because many of the higher reaches of human intelligence are letting the mind roam creatively and coming up with truly novel ideas. And that's just fundamentally different from the kind of reined-in task performance that we're assessing in these benchmarks. So yeah, I think they actually are very much missing something.
And do you think that that has to do with the kind of reversion to the mean effect of kind of going to the average that LLMs do? Or do you think this is just a matter of LLMs are just kind of going all over the place?
I mean, so this does come back to these issues as to how far is the kind of current technology going to take us in giving us intelligence. I mean, you know, true human creativity of new brilliant ideas is clearly extrapolating significantly beyond the bounds of what we know. I mean, I'm myself skeptical that large language models are ever going to do that, and you know, I actually do suspect we need more AI technology before we're going to get to system 2 thinking of an interesting thought, and that kind of creative thinking as part of that.
Thank you very much.
Hi, thanks for the very inspiring talk. This is Yusu from Ohio State University. I'm trying to connect the first and second part of the talk, and I totally agree that AGI should at least include a quick adaptation to an uncertain, ever-changing world. And then in the context of web agents, right? So the internet is one such world. There's like a billion websites out there that people can do virtually everything. And then it's ever-changing. So if, let's say, we have one day a web agent that can do almost perfectly on any website, given any goals from the user or itself, would you call that like some form of AGI?
Well, I think one wants to differentiate between being able to adapt and learn new things as opposed to just having seen everything, right? That the having seen everything approximately is this interpolation effect where it sort of looks like a simulacrum, right? That, you know, to some extent, obviously, humans sort of know how to operate websites because they've used some, and it takes a while to learn. So that's why it's reasonable to have a language model that has used some websites and knows something about them. But it's a fail if it then is shown, you know, a different website with some creative new ideas as to how it's laid out, and it can't adapt itself and learn to operate that one the same way a human being can. And so the question, I think, has to be this: we have novel, somewhat different websites or whatever it is, and that it's never seen before, and it still works. And, you know, the problem is that this is the thing that's becoming so hard to assess with a lot of the commercial large language models, because we never know what data has been put into them when we try and test them.
Thanks.
Hi, I have a question. It's Ying from University of Texas at Austin. So I like the example you give, Yuan LeCun. He says when people push the table, and this will never in the text. But the problem, the large language model transcends talking to people like we read a book. In the book, we can read a book because the book also couldn't see that the people move with the train, but it just describe it. Or there's many things not in the text, but we, as a person, we live in the world. We are referring. So semantics in the meaning, not on the context, also on where you refer. Because we can always relate those kind of text, hidden information with our normal life experience. So we actually can hiddenly understand many things. That's why humans read a book. But the problem, if you ask one large language model talk to another large language model, maybe the other language model never have a referring experience in their own life. They will not be able to understand that context. So that's, I think, if we still, human talk GPT, we still can feel the things which is not even written in the text. I just want to you comment on that.
Yeah, so there are a lot of issues. No? This one working? No. Yeah, so there are a lot of issues there. I mean, one is the issue of feeling and sentience. I mean, you know, sentience is often used to mean intelligence in a lot of contexts these days, but, you know, originally sentience was meant to be distinct from rational thinking. Sentience was meant to be feeling, and, well, you know, I think it's fair to say that our computers don't feel, and so if things are dependent on feelings in human beings, then the models don't have that. But, you know, the part about, you know, seeing stuff in the world, it's sort of a little bit unclear. You know, you could imagine if, you know, you can describe anything in language if you've got enough time. And so you could imagine a huge model could induce its own model of the physics of the world and the look of the world just internally to the all those parameters of the model, and it would be just as accurate a model of the world as the one you induce by seeing images, videos coming in your eyes of the world. It's not impossible to do that, but yeah, the question is whether that will actually prove to be possible. I agree with you that even though these models get better and better, it still seems at the moment that the models kind of have read about so many scenarios that in simple cases they can do physical reasoning and get them right, but it still sort of feels like it doesn't really understand in a system 2 kind of way, that it really understands the underlying principles. You know, and the question is how much that matters. I mean, this turns up in things like protein folding as well, right? That for 30 years people tried to build physics models of protein folding, and then AlphaFold said, oh no, don't worry about that, we'll just have a sort of a surface model of similarity, similar things will fold the same way, and it works brilliantly, but the feeling is, no, it doesn't really understand protein folding in a system 2 kind of a way. You want to stop now or should I play one more? Okay, one more question.
Okay,
go for it.
Last question. So I know, so this is Liang Yihuang from ASU, and I noticed that you use the Llama 3 8B versions. I want to know why you choose that, because in my opinion, the larger models always means the better performance. So in our lab service, we use 70B's Llama 3 versions. And in my experiments, I always perform GTP for O because this is larger. So yeah, so I want to know how you choose the language model size in your papers and research.
Because we're poor people at universities. I was getting kind of rushed at that point, and so I sort of didn't explain all the details. So actually the system used a mixture of different language models. So we were also using GPT-4o for generating descriptions, but the language model that at the end was the one that we were using to roll things out was an 8B model, and that was largely being chosen for sort of cost scale reasons. Obviously, you'd do better if you use the 70B model. Yeah.
Thanks.
Okay, I think you are allowed.
We have time for one.
Oh, okay. Hi, so I'll ask a very quick question. I don't want to wait for the excellent Mamba talk. Thanks for the talk, Chris. I'm Naomi, I'm from Harvard. And my question is just, with regards to your skepticism about large language models exhibiting system 2 reasoning, I'm curious about your thoughts on O1. In particular, I found it interesting that O1 Mini seems to be as good at math and coding as O1 Preview, despite being much smaller. But as expected, because it's smaller, it's does much worse in knowledge tasks. So I'm just curious on your thoughts on O1.
Yeah. So I obviously don't have a lot of secret information, but I agree it's impressive how well it does in reasoning. And this is, right, it's this linearization hypothesis that, it seems like it's showing surprising. I guess I kind of thought that what we were going to have was sort of some kind of marrying of the kind of tree-structured search that you saw in AlphaGo, etc., with large language models, where effectively what we seem to be getting is just we're doing a linearization of search exploration inside a long transformer sequence, and with whatever secrets they have of how best to train that, it seems to be working surprisingly well. I mean, I think the info is just that Mini is better because it's actually the sort of next generation model as the starting point for probably GPT-5, whereas the O1 is the sort of generation before one, even though it's a larger scale. I think is what's going on there. But yeah, it's as you say, it's impressive how well it works for reasoning.
Okay, we don't have time for more questions. So let's thank Chris again for the very inspiring talk.
Before we start, the authors of the stream of search paper, that's the third spotlight in the session, please come down here so we can check in with us.
Let's keep the excitement going. So in the following, we'll have 3 spotlight talks. So the first talk is entitled as Mamba, Linear Time Sequence Modeling with Selective State Spaces. So this paper was just received one of the 4 outstanding papers, and it will be presented by both Albert Gu and Tridal. Congratulations.